good. Hopefully you can all hear me and see my slide fine. So yeah, it's a pleasure to be talking to you, and I wish I was there in person, but unfortunately the pandemic raised its ugly head. But yeah, I'll be there in November. So if any of you guys want to catch up in November, I'm more than happy to meet with anybody who wants to. So yeah, tonight, as Tim said, I'm going to be talking to you guys about adding value through additive manufacturing. Before I start, maybe just one slide about the Creative Design and Additive Manufacturing Lab, which is the lab at the University of Auckland that I run. I describe it as a playground where companies, students, academics can come and really get their hands dirty with additive manufacturing. Until you pull parts out of a machine and have to do the post-processing, removing support material, you don't really appreciate why design is so important, to design the right way to maximize the benefits and the value it adds. So that's what we're talking about today, is adding value through additive manufacturing. And maybe just my first slide, I guess, is a bit of a reality check. And the simple truth is that additive manufacturing is expensive. Now, when I say expensive, I mean really expensive. It was probably the most expensive way of making anything in the known universe. So that means you only use it if you're adding enough value to overcome that high cost. But if you do, and you're doing it for the right reasons, you can add huge value to your products in a way that you couldn't before. And of course, I'm talking about additive manufacturing for production rather than prototyping. So making real products you can sell to the customer. Now, what is value? Of course, value is many things to different people, but one of the areas that, to my mind, additive manufacturing excels in, and one of the big advantages, is it can make products that are lighter. In fact, when you talk about design for additive manufacturing, weight is your worst enemy. Any material that doesn't serve real engineering functionality and add real physical value to your products, get rid of it. It'll make your parts faster to print, it'll make them cheaper, it'll make them lighter, and so on. So I thought I'd show you a real world example of this. This was two of our students, Taylor and Jake. It's a mountain bike brake caliper. So fairly simple parts. They've been around for many, many, many years. So what makes this one special? It's topology optimized, and it weighs 45% less than the aluminium machine brake caliper it replaces. We think, well, 45% weight saving on a mountain bike, who cares? Well, if you're a performance athlete and you're racing, that could be the difference between winning and losing a race. So as I said, weight saving, making products that are lighter is a huge advantage. Now, again, imagine if you have to ship these parts around the world. If you can lose 30, 60, 90% of the weight of the part, then you're starting to really add value by making them cheaper to ship around, making them better on the products that we'll end up with. Another big advantage besides weight saving is customization, making parts that are custom for you, the user. And this is, medical applications. Anything that you implant or has to fit your body is the perfect area of that. So this is some work we've been doing for the last just about a year and a half now on custom splints for, well, brakes and or, occupational overuse. So what you see on the top left is a scan of my arm, and it's a whole new breed of software that allows you to automate your design process. So you import a person's scan into the software, and you just tell it, I want to trim here and here, and in 30 seconds it'll generate you a custom prosthetic that fits you perfectly. And you can choose whether you want, Hello Kitties on it or a Voronoi structure. But again, the advantage, they're lightweight, so they're more comfortable. You can throw them in the dishwasher or wear them in the shower. And the single biggest advantage probably is that you can scratch yourself when you've got an itch. And believe me, that is a big advantage. If you've ever worn a cast and you have to reach in there with a ruler, it's not the best experience in the world. So again, maybe a more meaningful example of customization. This is a project we did just last year for Shaz Dag. So Sharon Dag is her name. She's a competitive kayak racer missing an arm. So we made a prosthetic for her, specially made for her to kayak. And it's got a ball joint on the end so that the end that's clasping the oar can rotate around like a real wrist. And she loves this. So this has improved her quality of life because it allows her to compete in much better ways than she could without additive manufacturing. So as I said, lightweight, Mass customization is another big area. A new area we've seen over probably the last 2 or 3 years, because of software changes, is increased heat efficiency, heat transfer efficiency. And this has come about because of these magical structures called gyroids. There's many others, but TPMS structures, triply periodic minimal surfaces. So these have been around for many, many, many years as mathematical ideas. But without additive manufacturing, you couldn't manufacture them. Whereas now suddenly you've got structures that are easy to make with additive manufacturing. And the other big advantage is they're self-supporting, which means you can print them with no support material. And what you see on the left is a single cell, on the right is a 2x2x2 cell. Now, imagine that in the radiator of your car. And the red side is a hot side, the blue side is a cold side where the water is flowing through. So what this allows you to do is it allows you to create radiators, heat exchangers that are much more efficient than the old plate and tube heat exchangers would have been. So what you see here are the radiator and a heat exchanger that we use on our Formula Student race car. It's an electric race car, and around the motors there's cooling jackets that we've printed as well with water running through them. And the heat exchanger you see there cools the water going into it. So again, what makes this special is it's much more efficient, and that means you can get the radiator down to about 1/3 of the size. So roughly 60 to 70% smaller physically than an old plate and tube heat exchanger, and lighter, which again is an advantage. And what makes this possible is this whole new breed of software that allows you to automate your design. So the two you see on screen there, they're automated. You design the overall shape in your favorite CAD software. You import that into the software we're using for this. In this case, it's called N-topology, but into the workflow. And in about 30 seconds, it'll automatically generate you a ready-to-print heat exchanger. And again, both of these are done with minimum support material in the print. And just to demonstrate that anything can be transformed into a heat exchanger, this is one we did just about 3 weeks ago. It's a little Pikachu, and we decided just for fun, we'll see, can we transform a Pikachu character into a heat exchanger? So the idea is the hot water goes in one arm and out the opposite leg, and the cold water goes diagonally across. And in this case, we took off the back of his head just to show that there was a gyroid in there. But as I said, this was purely done to show that absolutely anything can be turned into a heat exchanger. But the only reason to do it is because it adds value, because you get better heat transfer, you get lighter parts, which means in the case of a race car or a bus or an airplane, this is huge value added because it saves fuel, which means it's better for sustainability and so on. So as I said, those are just 3 areas that, to my mind, additive manufacturing just demonstrates that it adds great value, or enough value to overcome the high costs of printing. But as promised, and as Tim mentioned, I will talk a little bit about my 3D printed guitars. So yeah, I've actually been doing it since 2011. So that's a long time. That's over 10 years of making 3D printed guitars. And I started it really just to see if it could be done. Is it possible to make a printed guitar, not a prototype, but a real playable electric guitar? And I did my first one, and I did a blog about it because blogs were still popular 10 years ago. And I started getting emails from around the world, people who had never seen anything like that, and said, can we buy some? So I scratched my head and sold one, and I sold another one. So right now I've got on my desk in the room now, I've got 3 I'm building now, which will take me up to 99. And then the 4th one I'm building will take me up to 100 guitars, which is nice. And just to show you some of the guitars, and you can see all of these from a complexity point of view are complex shapes. If I was making a simple guitar, if I was making a standard Strat or a Les Paul or a Telecaster, this would be a dumb way of making it. Whereas because these shapes are geometrically complex, this is the only way you can make them. So the one on the bottom left, for example, has got New York City inside the guitar. It's got skyline of all the famous sites in New York inside a slightly kitsch American flag themed guitar. But the point is, you could not make this any other way. And just to show you a favorite, the one in the center, the gray one in the center is actually printed in aluminium. So most of my guitars I print using powder bed fusion, so laser sintering, and I print them in nylon and then paint them. The one in the gray one in the middle there with the flowers and the barbed wire, that one's printed in aluminium. And because it's always a favorite, the one on the bottom right, the steampunk, and all going well, the video will play. So if this is a steampunk, it's got gears inside, and what makes it special is the gears turn, because you can. Now, again, to hurt your brains, the guitar body is printed, assembled, ready to go all in one piece. It's not assembled afterwards. It's printed as you see it there. So printed in white nylon and then painted afterwards to give it the metallic look. So I think I'll show you my second to latest one. And hopefully that'll make the sound quality better. I know when the videos play, the sound quality goes a bit bad. So I'm actually a bass player rather than a guitar player. I play a little bit of guitar, but I'm a huge Beatles fan since forever, just about. So being a bass player, I decided to make myself a Beatles themed bass guitar. So this one, it's in the shape of a Höfner bass, which is the same bass that Paul McCartney is famous for playing with. And the music on the front is a score for Yesterday. And inside the bass, you've got iconic scenes from the Beatles. Yellow Submarine, of course, the Abbey Road scene on the left. It's got George Harrison's guitar on the bottom left, John Lennon's glasses. On the bottom right, I think I've got a close-up. You can see the drum kit from the Sgt. Pepper's Lonely Hearts Club Band album cover. Now, remember, this was printed in nylon, so white nylon, which means it has to be painted afterwards to get all the color in. Now, my wife is an artist, so she very kindly painted the inside of this for me. And I think that by the end of it, she was just about ready to kill me. I didn't design this to make it easy to paint. If you imagine, if you look at the drum kit on the bottom right there, it's got the logo, the Sgt. Pepper's logo, painted in gold and red lettering. And imagine trying to get in there with a paintbrush to paint that. It would be a complete nightmare. But she somehow managed to do it, and it came out, I think, personally looking amazing, and it plays great. It sounds great as well. But because of this particular guitar, I decided to give full color 3D printing a go, just to see what the possibilities were. So I designed this guitar, the Scarab that you see on screen here, and that is printed, well, it looks as you see it there, straight off the printer. So that wood grain, all the color, the dragonflies have got clear wings. That is printed as you see it there. So when it comes out of the printer, it's covered in support material. It's a soluble wax support material. So that goes in an ultrasonic tank to dissolve. And then I clear coat them just to protect them from the UV light. But that's it. All the color is as you see it there. And that is pretty amazing. I mean, being able to print in color, I was so impressed. So I got the guys at Mimaki and at Stratasys to print me samples to see what it was like. And I was so impressed with it that we bought one of the machines. So we have one of the Mimaki 3D printers in the lab. And because of that machine, we've now gone into a whole new area of work. So we're doing a lot of work now on medical models. So just to give you some examples of the kind of stuff we've been printing since getting the color printer. So you can see an artery on the left there where the doctor can explain to the patient what's going to be happening to them. Eyeballs, so prosthetic eyes on the right there. And again, a long learning curve figuring out how to coat them in biosafe material. And of course, a lot of work on surgical planning models, so models for the doctors to plan their surgeries. So again, those we call them anatomically correct Barbie dolls. Those are printed as you see them there with the clear and the color all printed together in one go. Yes, a little bit of post-processing to clean up, to remove the support material and then sand them and clear coat them. But that is pretty amazing to be able to work with that kind of a technology. Since then, we've been doing some more serious medical models. So we recently did one with a lady we basically did MRIs and CTs. She had a tumor next to her spine. So we combined MRI data and CT data to print a model for the doctors to plan their surgery to see how they were going to get to the tumor without hitting any organs. Now, it's not hugely new. That's being done around the world. What part of the challenge we had, I think the CT scan was for the bone data and the MRI was for the soft tissue data. But because they're on separate machines in different positions, it becomes a nightmare to combine the two data sets into one meaningful data set. So that took quite a bit of work to get that to work to the right level. But we managed to get it done. And again, the doctors love it. So we're printing more and more for the doctors. And just as promised, I said I'd talk a little bit about the wood printed guitars that George was playing in the Guns N' Roses jam. So, as Tim said, what makes this guitar special is that it's printed out of wood. It's sawdust and it's bio-epoxy printed onto the sawdust to bind it together. So it's the technology called binder jetting. For those of you not common, we use a powder base and then you print glue onto it. So in this case, the epoxy is made from lignin, which is another waste product from the wood industry. So this is a perfect example of additive manufacturing for sustainability. It takes product that would otherwise go to waste. Some of the sawdust and the lignin go to landfill or get incinerated, or at very best get turned into MDF. Here we're transforming them into high-value product. And yeah, I do think guitars are particularly high-value products. So there's no shame in owning too many guitars, is what I say. But as I said, so right now, this is just sawdust. So it's an American company called Forest who developed this technology. So at the moment, it's just random sawdust, but I've been speaking to them, and in the future, it may be possible to choose the flavor of sawdust you want for your reconstituted wood. So you might, for example, be able to choose maple sawdust or mahogany sawdust and reuse that to add, value added product. And the different colors, because they're printing bio-epoxy onto it, they can get 5 different inkjet printing nozzles to print different colors to reconstitute the wood grain. So as I said, this is just a very, very nice example of, making products more sustainable through additive manufacturing. So we've now got binder jetting systems in our lab, not for printing wood yet, though we will be doing that. We print mostly things like shell material. So mussel shells, there's a big problem around the world with mountains of mussel shells and oyster shells that go to waste and again get buried in landfills. So we're trying to print those into more usable products as an example. So really cool technology, binder jetting. For those of you who are not familiar with that, I would encourage you to investigate that, because pretty much anything in powder form you can print. We're doing ferrite with it as well, and a lot of other weird materials with these machines. So I'm just conscious of time, and I want to leave a little bit of time for questions. So I think I'll end it there and really just invite you guys to ask questions, I think via Tim, so I can hear what the questions are, or email me. My email address is there. By all means, feel free to email me. So I'll hand it back over to you. I think we got about 5 minutes for questions, Tim, so I'll hand it back over to you. And I might stop the screen sharing, I think.
Thank you so much, Olaf. Really, really interesting. And yeah, since we have a few minutes, anybody have a question for Olaf about the guitars or about what you heard?
Or anything else?
I have, of course, a lot of questions, but I want to leave it to you if you have any. Doesn't look like, you can think about it. I was just wondering, besides the fact that the guitar is now printed in recycled material, are there any other benefits from making a 3D printed guitar as opposed to a traditional one, or is it just because you can?
Because you can, because they look incredibly cool, but the big one is customization. Because it's a digital model, I can shift weight around to give it the balance you want. Now, I think George said this one is heavy, and I agree it is heavy. Most of my others are not that heavy. The next one I think will be much lighter. But being able to customize it so it fits your body, I'm not a small person, so I need a bit of a cutaway in the back to fit my stomach, for example. But being able to customize the instrument to fit you perfectly is a big advantage.
Yeah, about that. Another thing I would like to ask you about, because you're on the other side of the globe, and here in Scandinavia, the whole sustainability agenda is very, very present, and we have been talking a lot about it today, and we will continue to do so. how is the temperature in additive manufacturing where you come from when we talk about sustainability? Do they see it as a tool for that, or is it just an extra added feature?
Oh, no, I think now it's becoming a core feature of additive manufacturing. I mentioned earlier being able to make products easily 60 to 90% lighter. I mean, it's very few products that you cannot make at least 30 to 60 and sometimes 90% lighter. From a sustainability, that's huge. But also materials. I mean, New Zealand is a country that thrives on, we've got a huge wood industry, we've got a huge shellfish industry. Those are not going to last forever. So we've got to start looking at what do we do with all the waste streams from those industries to add value, to turn them back into high value products that we can sell to people around the world. So yeah, I think it's become one of the big core things in New Zealand. New Zealand is also a very sustainability conscious country. So maybe more so than some other countries, I suspect.
Good to hear, and hope to have you here someday. We can continue the discussion on sustainability. One final question: if I want a guitar, is it possible to buy one? No, I then we'll.
Yeah, look, I mean, absolutely. I do sell them. If you Google 3D printed guitars, you'll come to it's oddguitars.com. You'll find them there. And always we start a conversation because it's all about customization. I figure out what you want. I've offered people to scan their heads and put their heads on the guitar, their faces on the guitar, or even the knobs. But nobody's accepted that yet. But hopefully somebody will.
You never know. There might be one in the crowd here that will call you afterwards. Thank you so much for taking the time, Olaf. We really appreciate it.
Thank you all.